That's lecture 21. All right, so we're ready to start lecture 21. I remind you that there are two lengthy lectures, one on symmetric matrices and one on positive definite matrices posted. And I do not want you to even remotely think that the material there is less important than the one that I will do today on Wednesday or on Friday. It's extremely important, okay? As a matter of fact, I am going to use lots of ideas of symmetric positive definite matrices today, okay? So hopefully, you know, in order to address the homework set, you have to at least make an effort to go through these two lectures. So for my part, I need to really finish linear algebra at all costs this week. And there's a very high probability I'm only going to give one more lecture on linear algebra, and then on Friday start talking about differential equations. Simply because the material for this course is enormous, and if you try to do anything in any substantive way, we're going to run out of time. Okay, so today I want to talk about singular value decomposition, which certainly is, I will say, it's the most important decomposition in linear algebra, period, and it is the decomposition that is mostly connected with applications all over the place, okay? And applications are of the form of compressing images, for example, or doing model reduction in fluid mechanics or in any other area. So it's basically, it's the means to reduce the amount of information that you need to represent very complex matrices, okay? And you can think an image being a matrix, right? Because what is an image? If you pixelize it in a regular grid, it's a matrix. So do you actually need all the information in that matrix to describe that image? So singular value decomposition gives the answer to that. The same way if you do a fluid mechanics problem and you have a very complex fluid flow field running, you know, out of your, let's say, some fluid mechanics code, do you actually, when you look at it, you know what's going on, but do you need all that fine detail? If you don't, singular value decomposition will allow you to compress that information in a few rank 1 matrices. And we have referred to these rank 1 matrices multiple times in the course. All right, so to be sure that I don't run out of time with SVD today and we need another lecture, I'm going to go directly to what SVD is, how it works, you know, give you a proof and then give you two examples, and that will be the end of the lecture. But if you want, you can read more on applications. By the way, things like principal component analysis that lots of you will use in your research, they're directly related with SVD, okay? So when you go to your fluids courses and somebody tells you in your research, oh, you have to do principal component analysis, you have to respond, no big deal, I learned this in an intro course, you know, because really very elementary, you will see. But you will, the chances that each of you will have to use SVD somewhere, it's about 100%, okay? If you don't, you are looking at the wrong things. Okay, so what is SVD? If you take any matrix, all right, and that matrix does not have to be symmetric, doesn't have to be square. So if we have any matrix, we can actually write it with this very nice factorization, U sigma V transpose, where these matrices U and V are orthogonal matrices, which means they're square matrices, right? And their columns are orthonormal vectors, okay? So A can be a general matrix M by N, okay? So immediately from this decomposition, U is going to be an orthogonal M by M matrix. V is going to be an orthogonal N by N matrix. And sigma is a matrix that it's a diagonal that contains in the diagonal what we call the singular values of the matrix A. So again, U is orthogonal, V is orthogonal, and sigma is going to be a diagonal matrix. And this decomposition works for any matrix. Can you remind me, since you already read the lecture on symmetric matrices, what is the closest to this decomposition? I mean, when you look at it, what is the closest thing that reminds you for very specific matrices? How about symmetric matrices? What is the closest that looks like this decomposition for symmetric matrices? What do you have for symmetric matrices? What do we have instead of U? You remember U and V are orthogonal, so what do we have close to this? For the spectral theorem, right? So instead of U, we have the Q matrix. Instead of sigma, we have the lambda matrix of the eigenvalues. And instead of V transpose, what do we have? We have Q transpose. So there is only one Q, Q and Q transpose. Here, there is a different U and a different V. And I have not said that the diagonals of this matrix sigma are going to be the eigenvalues of A. No, they are going to be what we call the singular values of A. Now, obviously, not surprise, right? And I will emphasize it as we go along. If it happens that your matrix is symmetric, positive, definite, then this decomposition will be identical to what you learned with the spectral theorem, where you have a symmetric matrix being Q times lambda times Q transpose. So, but what you see there, it will be valid for any matrix A. That's not bad, right? Having any matrix and being able to write this decomposition that involves orthogonal matrices, that's significant. So A can be any matrix. Okay, well, I mean, I just see here immediately the statement that if it happens that the matrix is symmetric, positive, definite, then this is the decomposition. And since, again, you all spent time reading about positive, definite matrices last night, since I posted the lecture very late, can you tell me what's a positive, definite matrix? What is the simplest definition? That's a positive, definite matrix, all the eigenvalues being greater than 0. And the lecture, basically, that we posted, it only gives you some other elementary tests to check if a matrix is positive, definite, without having to compute the eigenvalues. Okay, but the definition is if lambda is greater than 0, then the matrix is positive, definite. Okay, so you will see why I'm insisting to bring this concept of symmetric, positive, definite matrix, because somehow in defining those diagonals elements in sigma, they have to be positive numbers. Okay, they will be the lengths of some vectors, so they have to be positive numbers. So really, we're looking for positive, definite matrices in this case. Okay. So what we need is we need two general orthogonal matrices, U and V. All right, and that's what makes this decomposition in many ways a very strange decomposition. Because somebody will say, I can see, having an orthogonal set of eigenvectors, but now we have two of those. Now, can you guess, just, we have a general matrix, right? M by N. Can you guess maybe why we may need two eigenvectors or, two sets of eigenvectors? I mean, the matrix is M by N. Potentially from where these two sets of orthogonal vectors are, these columns of U and V may be coming from. I mean, use your imagination, right? So A is M by N. So potentially from where do they come? How about the column space and the row space? Right? And actually, you are right. And some of them will be coming from the null spaces as well, because those are needed to cover the whole of Rm and the whole of Rn. But primarily, we're looking, I mean, if you look at the null space only, you'll be getting zeros, lots of zeros, right? So we're looking here some basis in the row space and some basis in the column space. All right. So this is a summary of what the singular value decomposition is, and then we will go in details to justify each of these arguments. So we have two sets of orthonormal vectors v and u, right, that form the columns of these u and v matrices. And here now is an incredible relation that the columns of u and the columns of v, they're related through this equation that looks like an eigenvalue problem, but is not. Look at that equation carefully and tell, of course, it looks like an eigenvalue problem. But why I say it is not? What is there that doesn't make this an eigenvalue problem? When I look at this equation, it says A vi sigma I ui. So why is this not an eigenvalue problem? What's an eigenvalue problem? Ax equal to what? Lambda x. So here what do I have? I have A vi equals sigma I times ui, another vector. Okay, so, but the relation between the vectors u's and v's will be given by this. This number sigma I will be called the singular values. And just to philosophize, and we will see this in details, can you tell me in what space is the vector v? So when you say A times v, to what space is that vector v? Remember, A is m by n. So can you tell me is v in the column space, the row space? What is it? I multiply A m by n with the vector v. So v is in which space? It's in the row space. So v is in the row space. And in what space is A v? So when you take combination of the columns, what space is A times v? In the column space. So here is an amazing result, okay? Without any proof or anything. It's going to come out that somehow we are taking a vector that sort of forms a basis in the row space, and by operating with A, we created a basis in the column space. So the row space is transformed to the column space, and from one basis in the row space, I go to another basis in the column space. And the reason, you know, this is a very lovely decomposition, because it connects everything we learned in this course, right? So now you really have to know about the row space and the column space, and obviously all the null spaces. But here is what's amazing. These v's are in the row space, and they're transformed through A to the column space. And if you ask me, wait a second, if I take A and I operate on an orthonormal set of vectors in the row space, why do I get a set of vectors U that they are orthogonal? That's weird, right? I mean, you take vectors from the row space that they're orthogonal, you operate with A, and you get U1, U2, U3. But I told you these U's are also orthogonal. That's not, I mean, it's weird, but it is the case. We need to prove it, of course. All right? So the decomposition has two bases to do this diagonalization. It looks like our spectral theorem, right? So A becomes a diagonal matrix sigma, but basically we need two sets of orthogonal matrices U and V. So we need to figure out how we compute those. And because sigma is going to come to be diagonal, will you agree with me if I write this matrix U as U1, the vector U1, then U2, U3, etc., and then I write the vector V transpose will have in each row the vector V1, the vector V2. Will you agree with me that if I expand this, this is what I get because the sigma is diagonal? Can you see that? I mean, I'm multiplying this and the sigma is a diagonal, so this is what I get. So you know what? This equation shows something extremely fundamental. By the way, what do you think R is going to be? you know, we talked about the basis of the row space. So what is potentially R? It's the rank. It's how many vectors, what is the dimensionality of the row space? What's the dimensionality of the column space, right? So obviously my V vectors, I will have R independent vectors, so R is the rank. So the expansion looks like sigma 1 U1 V1 transpose, sigma R UR VR transpose. So basically, I have taken, if you look at this equation on the bottom, this is an amazing result. We took this general matrix A, and we have written it as the sum of R matrices, where each matrix has what rank? These are matrices here, right? If you multiply a column by a row, each of this is a matrix. So what is the rank of each of these matrices? UV transpose. We have seen this hundreds of times. What's the rank of UV transpose, UV being vectors? Say it. 1, thank you. There was 1, by the way, for those who are listening to the tapes. So they don't think that, you know, we cannot say 1, all right? So we say 1. Okay. So we decompose this in R matrix of rank 1. That's significant. But there is something even more significant. These sigmas, all right, and we will show how we compute them, they are being arranged from the highest sigma value to the smallest sigma value. And that's where the value of the singular value decomposition comes, because effectively, if you want to approximate this matrix, what will be, if you want to approximate this matrix A with only one rank 1 matrix, which one will you use if sigma 1 is the biggest value? You will use the first one. So you go from a full matrix m by n, and you can approximate it basically with this matrix, that the only information that you need is 2 vectors. All right, so this is like capturing the main mode in the matrix A, and you approximate the whole matrix with sigma 1 U1 V1 transpose. Now, if that is not good, maybe you can approximate it with sigma 2 U2 U2 transpose. The amazing thing is that these sigmas, they decay way faster than the eigenvalues. So in most practical situations, if you use 2 or 3 or 4 values of this, even for a huge matrix, you're done. You don't need everything else. So effectively, this type of decomposition can be used to compress the information the matrix contains to much smaller information that is inside those vectors U1, V1, V2, V2, etc. Can you see that? And again, if I had plenty of time, I will bring for you some trivial images that somehow are being compressed with the singular value decomposition to convince you that even, you know, if I take a photo of you and I do a singular value decomposition, I advise you to actually maybe write or play with a MATLAB program to do this. You will see that if you do a singular value decomposition of your photo, just the first term will be sufficient to recognize it's me there. Okay? You may want to try it. 5 lines of programming. Okay, so that's the summary. All right, so I'm trying to see what is new. Okay, so here is, since we haven't really said anything about the null spaces, right? We said the vector V would be the basis of the row space, but if you take a vector in Rn, that vector has an element in the row space, but also has a component where? What's the orthogonal complement of the row space? The null space, all right? So obviously, you would need to add some additional V's, Vr plus 1 to Vn, from the orthonormal basis of the null space, all right? And you have to do the same thing with Ur plus 1 to Um from the orthonormal spaces of the left null space. the reality actually is you will never have to do those calculations because the corresponding sigmas to those vectors V's are going to be equal to 0. But if you want somehow to make the whole thing to be applicable to, to look nice in Rm and Rn, you can throw this basis, and I'll show you an example, all right? But actually, you're not going to gain any information because you will get 0 equal to 0, okay? So again, this is the only thing you will need. But if you want to make the matrices U and V squared matrices, all right? So we will need to extend those bases by introducing the remaining elements from the basis of the null space and the left null space. Okay. All right, so let's start and see how we prove all of this, right? And obviously, there's no magic, and the proof is not more than one slide. I don't know if it's going to be this slide or not, but it's OK. So let me take. So I am going to accept. I gave you this equation that looks like an eigenvalue problem. All right. For now, you can actually treat this as a way to define what U is given this orthonormal basis from the row space. You can take this as a definition, right? But there is no guarantee, as I mentioned, that if you apply A times VI, that you will get something in the column space, and those vectors will be orthonormal in the column space. There's no obvious statement why is that the case. But if we take this as a definition, so if we define AVI sigma UI, I can write this in a matrix form as you see this equation. Will you agree with me? So if I take A times V1 will be sigma 1 U1, and then A times V2 will be sigma 2 U2, and A times VR will be sigma R UR. And I can write this as the product of this U subscript R matrix times this sigma subscript R matrix, because I only use this, I only have R vectors in my basis in the row space. Will you agree with me? I can do this. I can rewrite this equation R times and get this equation. Okay, and there's nothing particular there. So now, if you try to, the way this equation is written, right? So remember, A is M by N. So this matrix V is going to be N by R. You agree? So it's not a square matrix. So it looks a little bit weird to keep track. It's N by R because the rank here was R. So we have R independent vectors in the basis of the row space. UR is going to be M by R. OK? And this matrix with the sigmas here is R by R. OK? And actually, you can see the algebra that works out, because if A is M by N, all right, so A times this V matrix, so M by N times R will give you M times R, and U times sigma gives you also M times R. So the sizes match. But again, this V's and the U's, I put the subscripts here R to emphasize that the basis that I have in the row space and in the column space contains only R elements. All right? So we will need to plug in there the basis for the null spaces to actually get rectangular U's and V's. So if you actually do this, and I'm going to give you, I think the equation is on the next slide. If you plug in next to those V's the basis for the null space, and next to those U's the basis for the left null space, you could actually make both the V and the U matrices to be rectangular. The only thing you need to do is, when you extend the sigma matrix in the diagonals beyond what you see here, you're going to have to put 0 elements, right? Because if you take A times a vector from the null space, let's say A times VR plus 1, by definition, that will give you 0. So you need to have a sigma element that is 0 to get a 0. Okay, so effectively, if you extend this and you add the vectors from the null space and the left null space, you get this nice decomposition AV equal U sigma, where the sigma contains this, this singular value, sigma 1 to sigma r. And I have not said what they are, from where they come, so we would have to explain that. But the bottom line is we can do this extension by adding all these zeros here in the right corner. Okay? And again, you don't really need to compute the basis for the null spaces. You only do them so that this equation looks nice, involving a rectangular V and a rectangular U. That's all. So it's very possible in the homework, for example, unless you really need to do it, you don't have to bother. You can even leave it blank, because it doesn't matter what you put in. You will get 0 equal to 0. Okay? All right. So this decomposition, of course, because these matrices V and U are orthogonal, you can, if you multiply on the right by V transpose, you get this singular value decomposition, the original equation that I wrote, that is A equal U times sigma times V transpose. Okay? So we know somehow if we start with a basis from the row space, potential is being transformed to a basis in the column space, right? This is what the claim here is. These scalars, both these vectors V's and the vector U's are orthonormal, so they all have magnitude 1. And effectively, the sigma values are, you know what? Can you tell me, let me look at this equation. A times V1 equals sigma 1 times U1. If V1 and U1 are unit vectors, can you tell me what is sigma 1? What is the meaning of sigma 1? So V1 and U1 are unit vectors. And AV1 is sigma 1 U1. So sigma 1 is what? Is the magnitude of which vector? AV1 equals sigma 1 U1. And V1 is unit vector, U1 is a unit vector. So what is sigma 1? Is the magnitude of which vector? So again, AV1 equal U1 times sigma 1. And if you take magnitudes on both sides, the magnitude of this is equal to 1. So sigma 1 is the magnitude of AV1. Right? So effectively, you know, the reason we introduced these sigma values is because we orthonormalize these vectors U1 to UR. You see that? We force them to be unit vectors, so the magnitude of AV1 is accounted by sigma 1 and then sigma 2 and then sigma r. Okay? They're sort of a scaling effect that we need to have in the equation. Okay, so we have seen all of this. Okay, now we need to actually start doing some proofs, right? The philosophy is good. So how do we get the singular values? How do we get the vectors V's? And how do we get those vectors U's? Okay? And again, I love this singular value decomposition because everything you learned comes back in this lecture. So it will show up that these singular values, the square of the singular values, surprise, surprise, they are the eigenvalues of A transpose A. And where have we seen A transpose A? Remind me, I forgot. In what problems A transpose A comes? Projections and a better word? More popular word? Least squares. All right? So it comes out that sigma square is an eigenvalue of A transpose A. And actually, if you calculate, you remember, even if A is not a square matrix, A transpose A is always a square matrix. And A transpose is a square matrix. So it comes out, actually, that both of these matrices have eigenvalues sigma square. So now can you see why we have to take sigma to be positive? Because, you know, we're going to have to take the squares of the eigenvalues of A transpose A. Right? And by the way, since you already read the lecture, or you will read it today, the matrix A transpose A not only is symmetric, but what else is it? A transpose A is symmetric plus also something else very powerful. It's squared, it's symmetric, and what else? It's invertible. Okay, that's fine. I'm looking for another word on the last lecture posted yesterday. And positive definite. So the eigenvalues, there's a guarantee that actually will be greater than 0, and that's why we can actually do the singular value decomposition, take square roots of those. If it was not the case, we were doomed. You won't be able to take the square roots. So in this case, we're actually being a little bit on the border. So we are going to say that A transpose A is at least semi-positive definite. So you can have a 0 eigenvalue, all right? But for sure, it's not negative definite. Okay, so it can have a 0 eigenvalue, but you know, the majority of the eigenvalues of A transpose A and A transpose will be greater or equal to 0. Okay. I don't need this. This is an example, actually, OK, so here's the proof. Let's take A transpose A, all right? You remember we wrote a decomposition of the form that A is equal to U sigma V transpose, and we said we want U and V to be orthogonal matrices. So we will now discover what they are, and we want sigma to be a diagonal matrix. We will discover what it is, OK? But we take the decomposition of A as U sigma V transpose with U and V orthogonal, and they are square matrices because we added, you remember the null space basis vectors also? Otherwise, I won't be able to do these operations here. So A transpose A will be the transpose of this times that. We agree? Now, if you take the transpose of this, what do you get? You will get V times sigma transpose, which is sigma, times U transpose, and U transpose times U is equal to, for an orthogonal matrix, what is U transpose times U? For an orthogonal matrix? Say it again. The identity. So basically what we get is, we get A transpose A is V times sigma transpose sigma times V transpose. And you know sigma transpose sigma is really sigma squared. It's still a diagonal matrix with the diagonal being the values of sigma squared, right? I mean, because it's a diagonal matrix. So can you tell me immediately, looking at this equation, half a line, this equal to that, tell me what V is. So it's an orthogonal matrix, but give me words. What is V? And remember the spectral theorem, all right, for symmetric and additionally positive definite matrices, but for symmetric matrices. So what is V? It's the matrix that contains in its columns the orthonormal eigenvectors of which matrix? A transpose A. Nice. So we know from where V comes. Is basically the eigenvectors of A transpose A. And what is each of the entries on the sigma transpose sigma? So sigma squared, what is each entry? Is the eigenvalues of which matrix? You remember when you do the spectral theorem, you have a diagonal matrix lambda. So sigma transpose sigma is like sigma squared, which is lambda. So what is each of the singular values squared is what? It's an eigenvalue of what matrix? A transpose A. We're done. Basically, we immediately have seen that by using the spectral theorem for square matrices, right, we recognize V to be the eigenvector matrix of A transpose A, and basically the singular values to be nothing else but the square roots of the eigenvalues of A transpose A. Done. Can you actually think without me doing the calculation? What do you think U is going to come to be? So U will be the eigenvector matrix of which matrix? A transpose. And what will happen with the eigenvalues? By a miracle, A transpose A and A transpose will have the same eigenvalues. Okay? The same eigenvalues. All right, done. I really don't need to do anything here. Then, of course, you remember we introduced so the use we said, basically the original sort of generalized eigenvalue problem was we take a vector vi from the basis from the row space, and we said A vi is sigma I times ui, and we said there's absolutely no reason why the vectors ui come to be orthogonal to each other, and of course of unit length. So here is the proof. If you take two vectors, ui's and uj's, and you use our fundamental equation that I stated that ui is avi divided by sigma I. You remember avi is sigma I times ui. So uj is avj divided by sigma j. And you do the multiplication, you get here A transpose A times vj. And you know what? I claim that A transpose A vj is sigma j squared times vj. Why is that? Why A transpose A vj is equal to sigma j squared vj? As per discussion 25 seconds ago. Why A transpose A vj is equal to sigma j squared times vj? Because we just proved before that vj is what? What did we prove up there? That vj is an eigenvector of A transpose A with what eigenvalues? Sigma j squared. So so what you get is sigma j squared divided by sigma I sigma j times vi transpose vj, but we started with an orthonormal basis in the row space. So vi transpose vj is equal to what? It's delta ij. It's either 1 if I equal to j, or they're 0 if I is different from j, because if you have elements of a basis, right, by definition, it's an orthonormal basis, so vi is perpendicular to vj. This thing here becomes delta ij, and this ratio for I equal to j, that's the only time you get a non-zero. They cancel, and you get that ui transpose vj equal delta ij. So the use vectors, by a miracle, come to be orthonormal. All right, and this is sort of very much surprising, and it's an amazing result in the singular value decomposition. So if you take an orthonormal base in the row space, you operate with A, you actually get an orthonormal base in the column space. This is, again, it's an amazing result. And again, we talked about A transpose, right? That will give me the use. And you know, we discussed the extension of this to account to extend basically the use and this to include the basis from the left and the right null space. So I am not going to repeat them. And eventually we have this extraordinary decomposition A equal U sigma V transpose. If there is something that you need to remember from linear algebra, is this singular value decomposition, because it contains everything, right? It contains ideas about eigenvalues, about the spectral theorem, about this orthogonality. What other ideas it contains? About least squares, an A transpose, an A transpose A, about the dimensionality of the spaces, about the orthogonal complements of the spaces, you know, the row and the column space being orthogonal complements to the null space and the left null space, respectively. contains everything, right? Contains everything. All right, since we're running out of time, let me see if I can find an example. There's nothing new there. So let me do one example. So I'm going to take an invertible matrix that is 4, minus 3, and 4, 3, all right? And I would like to do a singular value decomposition for this. Obviously, I mean, this is waste of your time, right? Because there are only, you look at this matrix, there are only 4 numbers to save. So really, singular value decomposition is not going to be helpful in any ways. But, you know, we are doing trivial examples in this course, so this is what we will do. So we need to do the SVD for this. Come on, where's my example? All right, here's the example. We do A transpose A, all right? So A transpose A, A transpose times A, I get this nice thing. And now to identify the matrix V and the singular values, what do I need to do? What's the next step? You have A transpose A, so what should we do now? Say it. Find the eigenvalues and the eigenvectors of this, all right? You can, you know, using whatever way you like, the 2 eigenvectors are 1, 1, and 1 minus 1. And you remember these are the V vectors. And you have, this is very important, you have to normalize them. If you forget to normalize them, all your calculations will go wrong. So your sigma values will come completely wrong. So you have to normalize them, right? They have magnitude 2. So this is 1 over square root of 2, 1 over square root of 2, 1 over square root of 2 minus 1 over square root of 2. And you have to find the eigenvalues of this. And the eigenvalues come to be 32 and 18. So sigma 1 squared is 32. And sigma 2 squared is 18. So you always put the sigma 1, you put the largest value of the singular values, all right? So the first one is 32, the second is 18. And obviously the columns of this matrix are independent, right? It's already square, so we don't need to add anything from the null space to these 2 vectors, okay? This is good enough. All right, so someone may be completely happy and say, the singular value decomposition of A is this matrix U, all right, question mark, we don't know what it is, times the sigma matrix, which is square root of 32 and square root of 18, times V transpose, all right? So this will be 1, 1 there, and 1 minus 1, all right? You take these vectors, and you make them row vectors, and that's V transpose, okay? So if you want to compute, you know, the U, maybe some of you, you know what you will do is, you will say, okay, let me do this multiplication. You know, so multiply this by this by this, and you better give me that, and you can fill the gaps there. I wouldn't recommend that, because you're not going to do that calculation if the problem is in, you know, 50 by 50. All right, but for this problem, you can just go and see what the values are in the matrix U. So generally speaking, what you will need to do is you will need to compute AA transpose, right? You don't really have to find the eigenvalues again. Why? Because they are the same. And actually, for this problem, you can see it comes by a miracle that AA transpose is diagonal. So really, the singular value squares, you can see immediately that they're 32 and 18. All right, because this matrix is a diagonal. And you can see actually that the 2 U's is, again, they have to be orthonormal. They're 1, 0, and 0 minus 1. The only thing, you know, here, for example, you could have taken U2 to be 0 and 1, all right? But if you actually take U2 to be 0 and 1, I mean, U2 will be 0 and 1 would be an acceptable eigenvector of this matrix, right? We agree? But if you do that, it happens somehow, if I can find it, when you plug in here 1 and 0 and 0 and 1, you will find out when you do the multiplications, you will not be able to match the signs properly. Okay? Because you remember, we want the sigma values to be positive, right? So you will need to do some adjustment in the signs of your U vectors to be sure that this works correctly, okay? So just what I suggest is when you do this, please double check that the signs match. So here is the answer that you see on the bottom. This is your original matrix. This is my U. This is the sigma matrix, and this is V transpose. And that's the singular value decomposition of the matrix A. Again, there is nothing fascinating because this example was an easy one. Let me see if there is an example where, okay, I don't, I think this example has also independent columns. So, you know, you compute A transpose A, you find the eigenvalues and the eigenvectors, and so the eigenvectors come to be 1, 1, and minus 1, 1, and the eigenvalues are 45 and 5. And so these are the V vectors if you normalize them. And so here what I have is I have another way to compute for U's. So rather than doing the eigenvector problem for A transpose, you remember we had this equation A V1 being sigma 1 times U1. So how about if I actually take A times V1 that we computed as an eigenvector of A transpose A equal sigma 1, which is 3 over square root of 2, we compute on the previous slide, times a vector U, and that vector U actually, I'm actually, let me just go back. What are the eigenvalues? Okay, square root of 45. Okay, square root of 45. I was misspoken here. So if you apply A on V1, all right, what you need is you need sigma 1, which is square root of 45, and whatever you have there, that is going to be your vector U1. So basically what you need to do is multiply A times V1, and then rescale the result so that square root of the eigenvalue from A transpose A comes on the front, and whatever is left is your vector U1. Because A V1 is sigma 1 times U1. All right? So again, you multiply A by V1, and then you get this result. That's what you get. So you're going to write this result as sigma 1, which is the square root of 45, and whatever you need to put there, that is U1. Okay? And then here's the answer at the end. All right? So this 2 by 2 matrix, okay? This is your U, this is your sigma matrix, and this is V transpose. There is an example, if I remember, that has the null space on it. So this is a nice example. Let's do it. Can you appreciate that this matrix is singular? Right? It has only one independent row and one independent column. Can you see that? So basically, when we do the singular value decomposition, and we will only be able to compute one V vector and one U vector coming from the row and the column space. And then we will have to enhance that information with additional vectors from the base of the null space and the left null space. So there's absolutely nothing difficult here, okay? So this is the vector that you get from your row space. It comes to be 0.8 and 0.6. Actually, can you see directly where 0.8 and 0.6 comes from there? What is the row space? That matrix has rank 1. Can you give me one vector in the row space of this matrix? Give me one vector on the row space of that matrix. Yeah? Which one? The rows are multiples of each other, so give me one vector, an independent vector in the row space. Will be what? 4, 3, thank you. And where did I get 0.8, 0.6? I got it from 4, 3 by dividing with the magnitude of 4, 3, because it needs to be unit length. Okay? Similarly, you can actually compute a vector in the column space, 1, 2, okay? And I divide by the magnitude square root of 5 to make this an orthonormal vector, a unit vector. So I don't really need to solve A transpose A on this problem. But you can actually do this because you will need to compute the singular values. So if you find the eigenvalues of this, it will come up that one of the eigenvalues is going to be 0 because this is a singular matrix, so no surprise there. The other eigenvalue is going to be 125, okay? And your decomposition is going to look like this. Now you're going to have to help me because it's 1120. So you remember, what is this vector 0.8, 0.6? Is one of the vectors we computed. And what is this vector 1 and 2? This is one of the u's. Can you tell me what is the vector 2 minus 1 and 0.6 minus 0.8? Because I have V transpose there. What are those two vectors? From where are they coming? From the left and right null space, basically. Okay? And you can go and check it, right? If you take, this is A, and you multiply with, all right, so let me see. So let me take this, okay? 0.6 and minus 8. If you multiply this matrix with 0.6 and minus 0.8, hopefully you will get a 0. Okay? So effectively, in this problem, we have to add, to make this matrix square roots, to make this matrix squares, we have to add an element from the left null space and an element from the null space of A. Okay, I don't really have time, it's 11:22, to continue an extremely interesting example where really singular value decomposition comes out with all its significance, so you may want to read it so that way I can do something else on Wednesday. Okay, so this will be the end, and I'll see you office hours tomorrow.